I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science. My name is Taylor Sparks, and I'm a professor of material science and engineering here at the University of Utah in Salt Lake City, and I am joined by Andrew. How are you?
Doing pretty well. A little bit tired. Haven't had my coffee this morning, but that will happen soon.
It is bright and early. Whenever you're listening to this, just know that we woke up. We spared no expense. No personal suffering is too great to bring you the greatest of episodes. And we are joined by somebody who is also taking time out of his busy schedule, Matt Cliffe, soon to be from Cambridge. Matt and I met on my sabbatical in England a couple of years ago, and he's the best. And he reached out to us and told us, hey, the Nobel Prize just happened for MOFs. We got to do a Nobel Prize MOF episode. And it was a great idea. Matt, how are you doing?
Really good, thanks. Yeah, really good. Just at a conference in Bordeaux, France. So this is even more international than you'd otherwise expect.
Absolutely. Bordeaux, France. That sounds wonderful in October.
Yeah, nice weather, sunny outside, good wine, good food, and some molecular magnets as well. But yeah.
So not a MOF conference, but you are a MOF researcher.
Yes, I am. Yeah, my research focuses on metal organic frameworks, and so we do a bit on the physical properties of these materials. But I'm interested in MOFs of all kinds as well. Yeah.
Okay. So the hook that I heard when I first learned about MOFs or metal organic frameworks is this notion that you've got a material that is extremely, extremely porous, right? And they'll say, like, what if a single gram of the material had enough, surface area to it that it could cover a sort of football field, right? I don't know if that's even a realistic analogy, but that's the one I heard. In other words, we've seen porous materials. Picture the sponge that you use on your kitchen at home. But what if you were to greatly, greatly, greatly increase that porosity? How would you make that material? What would they be good for? How would you characterize and measure them? That's all some of the questions that you dive into in the world of these metal organic frameworks. So we're going to talk about that, not just because the Nobel Prize, but because they're genuinely very interesting materials. I think they're in some ways at the forefront of material science in that we don't understand everything about them yet. We're still developing and learning new things about them. And they haven't quite hit the market and had the translational impact that some other more mature class of materials are. So that's what we want to cover in this episode. So Matt, get us started. When we say a metal organic framework, what are we talking about?
Yeah, so it's partly in the name. So they're materials which are made from metal atoms or metal clusters, connected via organic molecules to make extended frameworks, 3D or sometimes 2D materials. So you've got a metal cluster, maybe it's got one atom, maybe it's got, say, half a dozen or 12 or so. And that's kind of the corner of this network. And these are then connected by extended organic molecules, something maybe like terephthalic acid, 1,4-benzene dicarboxylic acid. These are nanometer length organic molecules, perhaps, into these open structures. So because you've got long organic molecules as your edges, that means there's a lot of space in the middle, potentially. So this is what, you're talking about a football field worth of surface area in a gram. And that's, so much as it makes sense to talk about surface areas that massive, you start getting to some philosophical questions. But the record, I think, depending on how you define it, is something like 7,000 meters squared per gram.
Holy cow.
Yeah. So this actually is 2 or 3 times more than the kind of most porous other kinds of materials, which are mostly activated carbons. But these are crystalline. That's probably most of the time MOFs are crystalline. They don't have to be, but nearly all the ones that people are most excited by are crystalline. So they're very, very well ordered as well, which people make use of too.
So you said something. You said that you've got either a metal or a cluster of metal atoms, and these are connected to organic linkers. So that's a very maybe well-known concept for the chemists in the audience, but for the material scientists, how on earth are you connecting a metal to an organic? Might feel a bit like, how's that happening? Do you want to describe that at all?
Yeah. So this is kind of through coordination chemistry, coordination bonds. So if you have a group that's negatively charged or has like a local negative dipole or something. So something like a carboxylate, so CO2 minus, that binds pretty well to metals. And sometimes these kind of things are used as isolated molecules to chelate metals, take them out of solution or whatever. But if you have two of these sort of carboxylate groups on either end, or three or four, those can act as the linkers. So it's that coordination bond. So they're basically, you've got negatively charged or able to or sort of locally negatively charged linkers that coordinate to your positively charged metal ion. So these are not in their metal 0 state typically, but in sort of metal 2+, 3+, 4+.
Okay.
And what sort of metals can you use? Are there any restrictions, or have been MOFs made with everything?
Pretty much everything, to be honest. I mean, so the most popular ones would be, as you might imagine, metals that are cheap and form these frameworks pretty easily. So things like zinc is probably the most. Zinc 2+, copper 2+ are some of the most well studied. As maybe we'll get onto later, there's a lot of interest in things like titanium 4+ and zirconium 4+ materials. But you can really get kind of anything in it. I know that there are groups who work with transactinides, so very radioactive elements, who've made MOFs for, I think, curiosity reasons rather than application reasons. I think there are plutonium MOFs, uranium MOFs, thorium MOFs out there. And you can even get edible MOFs made out of things like sodium and potassium.
What?
Yeah, I mean, are they MOFs? Are they more like a salt?
Huh.
Are they still like frameworks? But they're porous. They have metal ions and organic linkers. That's yeah. So you can make a MOF out of like a cyclodextrin type thing and potassium.
So I've got a question. Like, in my really basic chemistry understanding, right? I'm thinking about the charge dictates basically the hybridization of the orbitals, and the hybridization of the orbitals for organic materials dictates the number of bonds and the orientation of those bonds. Like, take diamond, right? Whether it's diamond or graphite or whatever, depends on whether it's sp2, sp3, and all that. Is that the same thing? In other words, does the charge of the metal ion dictate the orientation of the bonds, that these ligands that are going to be coming off from it, or is it not the case?
It's actually it's often a bit more like ceramics in some ways, right? These are pretty ionic interactions.
Okay.
So they're not necessarily at the metal side of things super directional. But what is directional? So if you take so they tend to have like the coordination numbers you'd expect to see if it's a single metal atom in like other kinds of inorganic materials. So like octahedral or tetrahedral, depending on the size of the metal and so on. But if you have a cluster, that actually allows you to get a bit more direction on it. So it's probably a little bit hard to describe
Oh, I see. So like the metal cluster has some orientation to it, and then the ligands just stick off of those, and so that's providing the shape, as it were, of the connections coming off of it.
Yeah, exactly.
Oh, cool.
Like whenever I saw MOFs the first time, it's this cubic kind of looking structure. I think that's often what you see in your first case, but turns out you can have tons of other different types of structures depending on that. And you can even have, is it possible to have multiple different metal centers?
Yeah, you can have the whole full range. So I think there's, people have done solid solutions with a kind of proof of principles of, I guess you maybe even call them high entropy, sort of half a dozen or so metals in it. You can also do using the different chemistries of different metals to kind of come up with more complex structures where one metal, say, is bonded to one end of an organic molecule. Say it's a carboxyl end, and the other one has a nitrogen end of the molecule. And you have two different kinds of metals bonded to two different sides. So you can kind of get into real complexity there. Yeah, if you want to.
Well, Matt, tell us about the history and the discovery. So many of the materials that we know and love were sort of observed in nature as like a mineral or sort of existing natural material, or they were accidentally discovered, or there's these typically interesting stories of how we came about finding them. Did these things exist in nature? Were they observed, or were they genuinely sort of built and had never been seen before? What did that look like?
So actually, I think so. The story of how MOFs, I guess, came to win a Nobel Prize is one of sort of chemists, I think, designing and starting from designing and building and coming up with concepts and building up new sort of structures. So if we take there's three Nobel laureates: Richard Robson from University of Melbourne, Omar Yagi, who's from UC Berkeley, and Susumu Kitagawa from University of Kyoto. And Robson did the earliest work on this in Australia, And he noticed that, kind of like we were talking about earlier, the metal atoms have preferred geometries. So he noticed that copper 1 has this preferred tetrahedral environment. And so if you coordinated it with another tetrahedral big organic molecule, then you could make a kind of expanded diamond type structure out of it.
Makes sense.
So you basically, by choosing a metal, choosing the organic molecule, you're dictating the topology of the structure. And because an organic molecule is massive, it means that the kind of gaps that you see in a cartoon crystal structure of diamond actually become real gaps that you can have solvent and other ions in it. Now, these weren't super stable, but he went on and designed various other topologies of materials.
Wait, did he actually synthesize those, or was it just like a pen and paper theory exercise?
No, they grew them. They grew crystals of
Oh,
them.
cool.
They solved the structures. They did various bits and bobs with them. But the problem with them is that if you try to take the solvent out, they basically fell apart. Like these are, the bonds were not super strong. It's only
Interesting.
1
So
plus copper.
the solvent actually stabilizes the structure?
Yeah, exactly. These are, when you grow a crystal of MOF, if you're doing it in solution, which you normally are, so much of the actual structure is the physical crystal you're lifting up is actually solvent by weight. These are really wet
Interesting.
materials.
I hear
in
we talk
some
about
ways.
them being like crazy porous, but like, what does that even mean if the solvent has to fill those pores to make up the structure? It's more of a composite at that point, right?
Yeah, exactly. And people actually started exploiting this, down the line for sort of ionic conductivity, right? If you can have a kind of solid structure that's full of liquid, or maybe you could use that for the conduction of mobile things inside it. But so the other two laureates started a little bit later in this, sort of mid-90s, and what they realized is that you should be able to make materials that are really porous, that do have empty space inside them. And so this required basically beefing up the strength of the bond. So one of the big things that Seiyou Miyagi did, as well as coming up with the term MOF, was realize that if you use a bigger metal cluster, you can often make the material more rigid. So the most famous material, though not the earliest one, is a material called MOF5, which is a zinc oxo benzene dicarboxylic acid. That's very, very porous, and it has that nice cubic structure that I think you mentioned, Andrew. But the first measurements of real porosity in it were done by Susumu Kitagawa, working on a slightly more complicated material. So that was again in the mid 90s. So they both, and other people, of course, around the same time, built on this, realized that you could take these materials full of solvents and then turn them into things full of empty space, and really massively expanded the range of different chemistries and different hence materials that you could make from it. And they've kind of been rolling ever since, just the number of structures going up kind of almost exponentially.
And what is the physical mechanism by which having, one versus a cluster of metal atoms strengthens those bonds?
It's kind of that there's just less flexibility around that initial cluster, I think is part of it. Also, the higher charge tends to mean that the bonds are stronger. So if you take like copper 1 and start pulling the solvent out of it, what will happen is that there's basically a capillary force as you're trying to kind of almost evaporate that solvent, and that'll pull the framework apart from the inside. So if you need to make sure it's relatively rigid, or at least is chemically rigid as well, so that it stays together.
So, Matt, these three people clearly made some important contributions, but as is, I imagine, always the case in these Nobel Prize decisions, you have to like draw the line somewhere, and people are always going to feel like, dang, I must have been on the bubble when it comes to LEDs, for example, right? Shuji Nakamura, the blue LEDs, them. Well, we had a guy in our department, Jerry Stringfellow, who won basically every prize he could win, but that one. He was instrumental in figuring out how to tune those. I wonder, are there a bunch of people in the MOF world like, did they get it right in picking these three people, or are there key names that you're like, boy, I would have thought that person?
I think probably these are the three that, talking to colleagues and stuff, these are probably the three that people would have been most happy with. Like there's not one person left out for really controversial reasons. Before he passed away, Gerard Ferret was probably the other person in kind of the conversation, and he was a kind of his big contribution as well as being one of the key early figures is that he came up with some of the earliest examples of flexible MOFs. So despite being crystals, that these can be really, really flexible materials.
Okay. So in diving in and learning about this, something that I think new entrants to the field will see right away and be puzzled by is these goofy names that y'all have come up with in this field. HKUST1, MIL53, right, on and on. Like, these are super bizarre. And we just did an episode on steel where one of the things we talked about was nomenclature and trying to understand what's driving this. Is there a system, method to the madness? So let me ask you, is there a method to the madness? Like, what does all this mean?
Well, there's some information in this. So basically, I mean, I think this is also one of this is kind of the naming conventions were kind of started by Omayagi as well. So all the materials that Omayagi discovered, his team are called MOF with a number after it. And initially that number was sequential, but now I understand that it is not sequential, and they choose numbers that for reasons that are completely opaque to those not in the group. But basically, there's kind of two broad ways that most MOFs are called some acronym. So MOF, MIL, my favorite, which is UIO, and then a number, right? And ordinarily the number ticks up, but it's, as I said, not guaranteed. So those acronyms at the beginning are typically actually the university or the institute those materials come from. So I guess this is a little bit like the naming of some mesoporous silicates, so things like MCM, if you're aware of that one. So Miller's Material Institut Lavoisier in outside Paris. UIO is the University of Oslo. That one is really confusing because many people very reasonably assume that it must contain uranium or iodine or oxygen, and in fact,
Nope.
it's a zirconium material. And you get a handful of other materials which are kind of given an acronym that tells you about the chemistry. So you can get ZIFs are probably the most famous, so zeolitic imidazolate frameworks. So these are materials containing the organic ligand imidazole, and they look a bit like zeolites in terms of the structures that they have. So it's basically a memorization exercise, unfortunately, but you can get a little bit of information about it. There's also some MOFs that have multiple names, which is usually for academic politic reasons and is completely unhelpful. But yeah, it is what it is now, and we kind of those in the area just have to kind of live with it and try not to contribute to the chaos.
Curious how this will evolve as computational design starts to be integrated into the MOF world more and more, where rather than it being somewhat of a rare event to discover a MOF, or maybe it wasn't all that rare, but it was at least limited by experimental capacity. Now, with the ability to design and find stable MOFs quicker than ever, do you think a naming convention will emerge?
I hope so. I think people love naming things after themselves or their groups, which is so that human thing's always going to be there. But yeah, I hope that there will be some more rational ways of approaching things. So one of the ways, the computational design, I think, is really an exciting aspect of things. And often the way they do this is by starting with the kind of structural topology that they want. So there's a series of relatively sensibly chosen three-letter names for topologies. So like the way that your nodes and edges are connected in space.
That makes
So
much more sense to me.
So you've got things like FCU for face center cubic, REO, which would be the rhenium trioxide structure, things like that. So you use these three-letter codes, and then you can give some details of the chemistry you've used to realize that topology. And so there's a few people, including me, who've used those kinds of codes to try and give a little more information in those topology labels, to give a little more information in the names of stuff. And hopefully that kind of stuff will be more widely adopted in future.
And material scientists, before you feel too smug about your naming conventions, we also have some goofball names. Spinel and Wurtzite, naming them after the minerals that they were found, is also pretty oddball, right? All right, so fascinating history. You think this is worth a Nobel Prize?
Yeah, absolutely, yeah.
How come?
I'm a MOF chemist. Well,
is that just because there's so many people that work in this field and they find it interesting, therefore it must be valuable, or why?
Okay, so I think there's a few things. So one is from a sort of chemistry sort of new compound perspective. These are really remarkable in the kind of design they do. You can go from kind of a sketch of what you imagine a 3D structure, atoms in space might be, and come up and using these kind of MOF strategies. There's what's Miyagi christened like reticular chemistry, reticule being like a net, like a fishing net, to design like where these atoms are going to be in space, and that seems really, really powerful. And if you're looking at, say, ceramics or something like that, it's often you're kind of just often just using the fact that there's a known compound nearby to do it. It's much harder to come at those kind of design rules, whereas MOFs do have that ability, and this sort of modularity is really exciting for not just coming up with cool structures, but being able to tune the properties as well.
Okay.
The other reason I think is that they have really very, as we touched on a little bit, really unusual physical properties, very, very high porosities, porosities with like different kinds of pore, not only the voids, but the edges of the pores can have all kinds of interesting chemistry on them. They've got very high flexibilities, as I mentioned, so really large despite being crystals, really large thermal expansions, really high compressibilities, negative thermal expansion, negative compressibilities, things that shrink or expand when you take up solvents. Crystals changing in volume by 100% or something.
Oh, gosh.
There's a lot of very strange things going on in these materials. So I think that's,
in other words, like it's a complexity argument. You think like because these are such a massive design space with so much tunability, tailorability, it's worthwhile to make a Nobel Prize out of it because it's such a big new area.
Yeah, and I think really all three of the laureates were people who recognized this idea of design.
Yeah.
Not just that these are, because actually if you go back and look at the databases of crystal structures that are known, you find materials that are pretty plausibly MOFs, right? They're compounds that could that could be now categorized as that. And in fact, you asked early on, are there were these discovered in nature? And they have been, but only about 10 years ago. There is some rare Russian biogenic minerals containing oxalate that happen to be MOFs. But it's not that the compound exists, it's that we know and we have these strategies for designing materials, which I think was the really exciting aspect of it.
All right, Matt, so you've said before, we're thinking this a little bit like Legos, right? You've got building blocks, you've got the metals, which are the vertices, the corners, you've got the linkers, which is these organic molecules, and then you can also have functionalization, right? So as you were to swap out different metals or different ligands, like what's driving that? What options do you have? Like what choices do you have? Like why would you choose one linker over another?
So there's this kind of straightforward thing. So you choose if you take a ligand that makes a MOF and you make a longer version, so it has the same geometry, the same binding group to the end, but it's just bigger in the middle. Maybe you've got one and add an extra benzene ring. You'll make it more porous. You'll make it more open. And people have explored that. In fact, that's now very, very standard kind of thing you can do. That's one side. But probably more interesting is you can add, do organic chemistry on a ligand and put on reactive groups. And those reactive groups you could either use as tags for other things, or in fact, they'll infuse the gas sorption properties. So, for example, if you put, so most of the time the MOF ligands are basically hydrocarbons, aside from the bits that bind to the metals on the end. But if you put something like an amino group, an NH2 group, that'll often bind with gases much more strongly, so allow you to have selectivity for one gas over another. And that's something that's really being explored at the moment. There's obviously a lot of desire, and I think you covered this in a previous episode, like to get sorbents that not only have large uptakes overall, but can specifically separate one gas over another. If you can strip out CO2 specifically from the air, then that'd be really exciting in terms of reducing the effects of climate change.
And adding something like an amine group or a benzene group or whatever else, right, also affects the rigidity, right? The mechanical properties of those linkages. And you'd already mentioned before that some of these things are flexible or not flexible. I imagine that plays a role.
Yeah, for sure. If you make it longer, it tends to make the material floppier. It's as straightforward as that.
Yeah.
You could do kind of wackier things as well, like people put photosensitive groups in it. So there's various sort of chemical groups that are known to change shape, benzenes that change shape when you shine light on them, and people looked at materials
Oh,
that way. And
okay. I've seen these sort of
so
molecular motor sort of things where you try and get functionality via light.
yeah, exactly. That's actually a current topic for a few research groups at the moment. I know. Yeah, but there's really the full range of kind of things you can do in organic chemistry. If you put binding groups on either end, you can probably get it into a MOF and then explore what this organic molecule does in this crystallized material.
In doing some preparation for this episode, I came across a number of people who were really interested in using MOFs to basically devise atomic microreactors or nanoreactors or maybe angstrom reactors where you can now do particular reactions within the MOF pore on a singular molecule or perhaps on a protein itself. So I know a lot of people are interested in that. Are you familiar with any research in that realm?
Yeah, there's all kinds of different things. So I guess the material that I haven't I've only kind of mentioned in passing, but is kind of the forerunner in terms of porosity would be zeolite. So these sort of very porous silicates. So they tend to have lower porosities, a less a more restricted range of chemistry, but they're really widely used. And one of the reasons they are is because they're catalysts and they are able to have reactions happen inside the pores of those materials that are very hard to do otherwise. And this is, I think, a goal of a lot of MOF chemistry as well. So either using the framework to as functional groups on the framework to catalyze reactions, or even just the confinement effects of squishing two molecules that want to react together in the pores. That's something else that people explored. Equally, people have done stuff like if you can trap something bigger inside the pores of a MOF, it can often protect it, from the outside world and keep it together. So proteins would be the example that people are looking at there. Proteins and other kinds of biomolecules that can often be fragile on their own outside of solution. Sometimes design them off or come up with them off that would help keep them safe.
Oh, that's really cool. Yeah, I think like material scientists, like we've got our little tiny acrylic, tiny sample holders. It's cool to think of a molecule, as it were, as the sample holder for some other substructure. That's really cool.
Yeah, it's a really neat idea.
And before we move on, what is your research in MOFs?
Yeah, so I don't really look so much at the porosity of things. So as I said, like I do physical properties, and what I mean by that is kind of looking at the magnetism and conductivity of these guys. So the metals are far apart, but actually, and the metals are often where the magnetism and conductivity is. But the organic molecules can themselves have unpaired electrons, have spin and charged as mobile, and that really opens the door to a lot of different interesting behavior. So room temperature ferromagnetism, metallicity, these have recently been found in MOFs and related materials. So we're kind of looking at MOFs as quantum materials, basically, using that modularity that I kind of the idea that you can tune it.
How do people characterize these? X-ray diffraction comes to mind, but could you see these structures in like a TEM?
Yeah, so X-ray diffraction is the standard, right? So these are solid materials. So X-ray diffraction allows you to see the crystal structure. We can solve the structures from single crystal, or in favorable cases, powder diffraction, and work out where all the atoms are and move forward from there. But as TEMs have improved, actually you can get atomic resolution images of these MOFs as well. You can see the pores, you can see the metal clusters and organic ligands that make the materials up. So in fact, you can even see defects in these materials. So sometimes you're missing a series of ligands or organic molecules, or you're missing a series of metal clusters, and you can actually pick that up in the TEM now. So yeah, you can visualize it really directly, as well as using these diffraction-based techniques.
So microscopy, X-ray diffraction, but you mentioned an odd one previously when we were talking about this, that people rely on BET, right? So that's Brunauer Emmett Teller. It's a porosity measurement. It measures surface area, which I wasn't surprised because many of the applications of this are reliant on the surface area. But you point out it's not just that. It's that the porosity, if it's very low, that's an indicator of impurities, right? Because the MOF structure itself, you expect it to have a high surface area. So they'll do sometimes these BET measurements to tell you essentially something about the purity. Like, did you get the pure MOF, or is there a bunch of not porous other stuff in there, which I thought was super cool.
Yeah, exactly. So like if you're thinking of say a typical MOF where they have like 2,500 meters squared per gram surface area, you know it's going to be that because you've got the crystal structure. You can have a rough geometric guess on what it should be. If you measure your material, you think you've cleaned it out pretty well, you've activated it in the jargon, and then you measure the surface area and it's only 500 meters squared per gram. Either you've got a lot of stuff that's not your MOF at all there, and it's only a small fraction of it, or your MOF pores are full of all kinds of other molecules, maybe solvent, residues of the synthesis. So it's one of those techniques that is harder to if you get a high surface area, then it's really telling you that you have the material that you expect to a large extent. I mean, interestingly, actually, mentioned defects. Sometimes you get to the you get the opposite. You have a higher surface area than you should, right? You look at the crystal structure, the perfect crystal structure, and the surface area is bigger.
Yeah. Hold on a minute.
Yeah, and that's often because you've got these defects. You're missing parts of your material. There are bigger pores than you expect, and that can be a sign of things like that. But that's a kind of special case.
So one thing we looked in the literature getting ready for this episode is, I think it was Kitagawa's group. They did BET measurements, right, as you do, to figure out pore size and that. But they found something that during these absorption isotherms, there is this what they're calling a gate opening behavior during these flexible frameworks, where essentially it's a signature of these soft MOFs where the structure can open in response as a function of the pressure of the gas around it.
Yeah. So this is one of the kind of weird things that is mainly seen in MOFs. I'm sure people have found it in other kinds of porous materials afterwards, but it's kind of a real signature of these sort of materials. And that, so basically it's saying that the MOF binds strongly enough to that gas that it is able to overcome the lattice stiffness to just change its crystal structure, go through a phase transformation to a different phase. So you can sort of think of it. I don't think these were the initial Kitagawa ones, but some MOFs look basically like wine racks. So they have sort of a square grid almost, or where there's very rigid edges with flexible corners. Right, so a wine rack you can flatten down, and in fact, if most of those sort of wine rack materials, often you make them, they're in that kind of closed form. They're the kind of form that you'd store in your garage or whatever. And then if you put CO2, a reasonable pressure of CO2 or water or some whatever the gas your material responds to in, they'll just open up, and this is a very dramatic change, and leads to very clear signature in those porosity measurements. The interesting thing there is that it seems to be a quite specific phenomenon. So very often, say CO2 will open it because it binds relatively strongly compared to something like nitrogen. So you could perhaps use this idea to selectively take up CO2 over nitrogen.
Oh, interesting.
And that's one of the real one of the reasons that people have really pursued these kind of gate opening transitions.
So we've been skirting around one of the key issues with MOFs that we've got to dive into, which is, you've said, like, these are flexible, they can move, there's this gate opening mechanisms. All this sounds great from a functional standpoint, but what the problem lurking in the distance is that maybe these things aren't as stable as they need to be. Is stability a real issue? Tell us about that a little bit.
Yeah, stability is definitely an issue, right? But it's one that has been worked on quite a lot. So and that's been kind of there from the beginning. People have realized that these materials aren't quite as stable as you'd ideally want. So MOF5, that Omeyagi material, zinc BDC material, is really exciting because it's really thermally stable for a MOF, like 400 Celsius. Yeah, but or for an organic containing thing, it's pretty stable. But that one is pretty sensitive to water, so it'll start turning to a hydroxide. And that's about 25 years ago that material was first discovered, and people have now come up with strategies to make materials that we can reasonably expect are going to be pretty stable in not only to sort of similar sort of temperatures, 400, 500 Celsius, but also in acids and bases,
cool.
and relatively aggressive conditions. And that often is using like higher charge metals. So the
just
UIO,
increasing the ionicity, right? Increase the bond strength.
Yeah.
Yep.
Yeah, exactly. Just crank up the charge to make the bond stronger. So these zirconium ones, and also it seems that if you have more hydrophobic organic molecules as your connectors, that tends to increase the stability as well, because it just means the water won't go in as much and won't start attacking those metal organic bonds quite as much. So that seems to be the other big thing that people do. So not every MOF is stable, and something that people, you still check it. When you're making material, you're still checking it, but it provided that you don't need really high temperatures where your organic is going to just start burning, basically decomposing, or really really aggressive conditions. There will probably be a MOF that will be stable in the conditions you're looking at nowadays.
So maybe we can transition a little bit to what these could be used for. We've touched on it a little bit with absorption or maybe gas storage, but what are some other interesting applications for MOFs, and what are people trying to design for?
Yeah, so still I think the main one that people are looking at is gas sorption separation. So all kinds of different separations people are trying to optimize, CO2, nitrogen, I mentioned, things even more exotic ones like hydrogen deuterium, that kind of more niche application too. The other, I think, big application at the moment that people are looking at is catalysis. So using these MOFs as catalysts to selectively speed up particular reactions. Whether this is sort of more on the organic scale, if you're sort of an organic chemist, you want to have a kind of small scale catalyst to use, or something more on the industrial scale. So things like, there's a lot of people looking at things like photocatalysis and like water splitting and so on. I mean, I think one of the more advanced areas that there is sort of a bit of, it seems that these MOFs are pretty good, is trying to combine the two. And this would be things where you have a sorbent which is trying to decompose the molecule that it's absorbing. So the sort of example of this would be sort of chemical weapons, right? So if you want to, you want something that's going to not only filter out the dangerous molecule to stop you from breathing in, but also decompose it.
That's so cool.
There's a handful of MOFs that seem to be able to do this pretty effectively.
Is that an electrochemical process, right? In other words, does the MOF backbone have to be conductive?
No. These ones just work. Basically, they specifically. So a lot of the chemical weapon things are relatively reactive in a specific way. That they have to react with something in your body to cause the damage.
Makes sense. Yeah.
And they are able to kind of mimic that, speed up that transformation, often with water. Just making them react with water and turn them into something much more benign. Overall, but that's how they work. So you don't actually, at least the ones I've seen, you don't need to hook them up to a circuit or anything. They're just a kind of passive device that you could put into a filter.
Yeah, the other one I'd seen is for natural gas vehicles. I guess storing natural gas can be pretty challenging, but with a MOF being able to store it in the porosity, it can actually compress these molecules and allow you to increase the amount that you can store in a given tank.
Well, and it lowers the pressure, right? Like the tank cylinder doesn't have to be at a high pressure because there's a chemical absorption, right? Reducing the physical pressure of containing that gas, right?
Yeah, exactly. So, I mean, it's a bit counterintuitive if you say it like, we're taking this gas tank and then we're going to fill it up with something else, and that will allow you to store
reduce
more
the pressure.
things in it. Yeah. But yeah, that's it. It's the fact that your methane will just stick to the MOF better than it does to itself. And so it reduces the pressure that you need for it. And this is, they've gone as far as making, I think BASF have made methane tanks containing a MOF to show that you can produce it. I think methane vehicles have not sort of taken off, particularly with like the success of batteries, but that is definitely, that kind of big scale gas storage is one of the things that people use for.
Oh, I was just going to say, I mean, like people have been talking about this with zeolites for a while too, but my understanding is it's about how easily you can, not only how easily you can store the gas, but how easily you can get it out as well. I think zeolites, it takes pretty high temperatures to do that.
Yeah, so when you're thinking about these absorption processes, there's always a kind of fine balance. I think hydrogen is sort of the example where it's really tricky, because hydrogen doesn't interact very strongly. In some ways it's like a molecular helium. So it doesn't interact very strongly with most absorbents. And that means it's very hard to get a large amount of hydrogen into a material except at very high pressures or very low temperatures, right? But there's lots of chemical ways of storing hydrogen where the hydrogen is really strongly bonded. So basically molecules that contain hydrogen that you could decompose to release that hydrogen. So ammonia boranes and things like that. And so those will have the high capacities that you'd want. The hydrogen as a percentage of mass of the material is pretty good, but it's impossible to get out. So there's this kind of trying to find materials that are in that middle space where they have strong enough interactions where the gas you want sticks in, but weak enough that you can get it out again without having to go to like 500 Celsius or whatever is the real challenge. And I think the hydrogen in particular, that one still seems to be quite tricky.
So we three academics are clearly like great at brainstorming potential uses of this, but are companies biting on it? Like, are they actually manufacturing large scale production of MOFs?
Yeah, there are definitely large scale manufacturing of it now. I mean, depends what you mean by large scale. So I think thousands of tons seems to be about as much as people have made of some of these materials, which is plenty for lots of applications. In terms of the sort of applications that people are looking at, one of them is, I think, Numat in the US, where they're using MOFs, the same kind of gas tank idea, the same, but rather than storing methane, storing high purity gases for semiconductors. So these are often very toxic, things like arsine, don't really want like as in your lab at all unless you really have to. So reducing the pressure of it means that they can become a little bit safer. I think is the basic idea there. Other kinds of applications that I think have been explored, like are using to store things like ethene and plant hormones to regulate the ripening of fruits, so you can store them for longer. I think particularly apples, people looked at that.
I've heard that, right? Isn't it ethane gas causes it to mature more rapidly?
Yeah,
and so essentially, if you absorb that, then you've extended the shelf life of the fruit.
Yeah, I think that's the idea. It's basically the reason why if you put bananas in the fruit bowl with other fruit, everything starts going riper a lot faster. So it's the same kind of thing, but in reverse. I think the big potential application that a lot of people are excited by is probably two. One would be water harvesting. So using MOFs that have high affinity for water and using the fact that, so if you're in a desert, right, I guess, well, I don't need to talk to people in Utah about that. There's you can often get very big temperature swings, and you often need water. So the idea would be perhaps overnight your MOF will take water out of the atmosphere, and then just the heat of the day will then release that water back out again. So you could use that to effectively generate water from the ambient humidity, even if it's relatively low. So that's one application that people are looking at on a larger scale. And the other one is things around carbon capture, right? If you can get direct air capture, so capturing CO2 out of the 400 ppm that's in the air, that would be really exciting. But that's both a really hard challenge, sort of academically. This is a quite low concentration, so you have to be really selective to pull it out. But also is, I think, a big industrial challenge because there's a lot of CO2. Even if it's only 400 ppm, there's a lot of air on Earth, and so to have a meaningful effect, you're going to be making this on an enormous scale.
Yeah, I think it obviously makes much more sense to capture it where it's concentrated at the polluting site, right? At the smokestack, right? Put it in line with that, and you're going to do a lot better.
Yeah, and there's also people looking at that as well, of course. Yeah, those are some of the kind of bigger scale things that people are looking at.
There seem to be a lot of promising applications, and in many of the demonstrations I've seen, MOFs have shown success. So what do you think really is the limiter here that's kind of preventing a lot of these interesting academic discoveries from having greater market penetration? Is it the processing of the MOFs themselves, the scaling of those from the benchtop to an actual production process? Or is it something else? Do we still not really understand the chemistry as well as we need?
I think probably the first two that you mentioned are the bigger things. So most of the time you're making MOFs, you're making them as loose powders, and loose powders is rarely the application you really want. They're rarely the sort of form of material you really want. If you want it for gas separations, you probably want it as a membrane. If you want it to storage and you need it to have something that's going to not just like leak everywhere when you pump things in and out. So people pelletize it to make it kind of more stable, and you have to think about how stable your pellets are and all that kind of more practical thing there. The other side is, as you say, scaling. So like the classic way of making a MOF is heating up your metal salts in maybe a metal chloride or nitrate, which are often acidic, in a solvent like dimethylformamide, which is toxic and really not a nice thing to handle on particularly if you're going to be doing it on a massive scale. So people have had to come up with ways, and they are, of getting rid of some of these more challenging features and getting the yields up. I think, yeah.
Yeah, did the synthesis processes affect the quality of the outcomes? I have to imagine they do. So you have a target structure, right? But maybe that structure will still be maintained depending on your synthesis route, but you might have more defects.
Yeah, I mean, this is part of it. You've got to you can't just assume that the material. You can't just that's it. You can't just assume that you're going to get the material you want if you change the synthesis parameters. You'll have to do the kind of quality control to make sure that your structure and physical properties or chemical properties that you really desire are still there when you change the parameters of your synthesis. And I think maybe part of the reason why there's this challenge with scale up is just that we haven't, this hasn't been done very much at all. So we don't have the kind of, if you take like other kinds of classes of materials, we've now got a lot of experience in what kind of things are going to be really important, how you can get it on the scale that you need, and also critically, people have an idea of how much it'll cost. MOFs are expensive at the moment generally, but part of the reason they're expensive is
the metal, or what's driving the cost?
Well, so yeah, I mean, it is possible. So if you decide to make a MOF out of gold, then it's going to be expensive, or some of the rarer metals. That's you can't get around that. If it involves something if it has an ingredient like that is expensive, but a lot of it is that just the preps aren't optimized because they're done on such a small scale. If you're making, in my lab, making a gram would be something we'd like gear up to. We start with much smaller scale. So of course the cost of that is going to be if you worked it out would be just unviable, and we don't know how cheap you can if you make a material in a lab. It's not obvious how cheap it will be if you did it properly on a ton scale,
for sure.
And as the experience in kind of a scale up happens, then people will be able to say, "Oh, this MOF, you can probably make that for how many dollars a kilo or whatever." We don't have it yet.
My final question for you, Matt, is I'm going to have you pull out your crystal ball for a minute, right? You've been to the conferences, you talk to everyone. What's at the frontier of this field? Like, what's coming down the line that excites you?
I think, first off, I guess I would say this, but I think some of the things in terms of the magnetic and electronic properties of MOFs are still really surprising. I don't think we've reached the kind of limit of where we can get there. I think they're going to be, as well as with materials with higher conductivities, higher ordering temperatures, there's probably going to be some pretty weird things. In the same way there's some pretty weird ceramics with magnetic properties, there's probably going to be MOFs doing that. I think also it seems that we've now reached a point where MOFs are actually getting used industrially. They are getting, companies are spending serious money trying to not only make but also buy these materials and put them into applications. And that's, I think, going to have an effect as we realize where the actual challenges are. Like, it would be less academics saying this is probably going to be useful, and more, companies saying, actually, we need this. Yeah. So I think that's going to be probably a change over the next few years.
Matt, you're amazing. Thanks for joining us. Thanks for suggesting the episode. By the way, listeners, love that. Reach out to us. Like, we love to interact. You can find us all over the place. We're on Instagram. We're on YouTube. We read the comments. We love it, and it helps us come up with better shows. Matt, I hope our paths cross again. Hope we see each other soon. And if not, enjoy the rest of your stay in Bordeaux, and we'll see you next time.
Cheers. Thank you very much for having me.
If you've been listening to the last couple episodes, you've probably heard us talk about the American Ceramic Society and their great on-demand learning center. If you're a technician or an early career scientist, or maybe you have a lot of experience and you want to learn even more about ceramics and enhance your technical expertise and your know-how, this is a great way to do that.
Yeah, one thing to point out is we have been really excited that they offered a special bonus for our listeners. You get $100 off of any on-demand course registration, but that is until the end of the year. So time is short. Sign up while you can get that sweet benefit. And they've actually got some new content on there. For example, there's new additions to the lineup. They've got an intro to electronic ceramics, a technician's guide to ceramics, and a foundations of ceramic processing. All cool courses in addition to the many that are already out there. You can use the code Materialism and you'll get $100 off your registration till the end of the year. So check out ceramics.org/materialism and go learn more.
The Materialism podcast is also sponsored by Materials Today. You can visit materialstoday.com to stay up to date on the latest happenings in the material science field and read some of the fantastic articles that they've published. You can also head over to elsevier.com to find out more about their journals, books, conferences, and related programs.
And as always, we are so excited to have you guys a part of the show. I just got back from a conference where I met with so many listeners. It is absolutely unreal to be connecting with audience members from around the world. We would love to hear more feedback on what stuff you guys want to hear. You can find us at materialism.podcast@gmail.com or the @materialism podcast on Instagram, or pretty much everywhere you want to find us. We are out there and we love hearing feedback on the show. Special thanks to the people who make the music possible for this show, Alphabot and Kolobyte. We appreciate you. And that's it. We will see you guys next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.